Hello everyone, my name is Sahar Mehpoor and I would like to present our paper RulePad Interactive Authoring of Checkable Design Rules. Developers have long been encouraged to use documentation to learn about software design and to make sure the code changes are consistent with the documentation. But the problem is that documentation is often distrusted and out of date. The reason behind that is that documentation and code are disconnected. So we propose an approach to connect documentation and code by integrating them, and we call this approach active documentation. In active documentation, design rules are translated into checkable constraints, and an active link is created and maintained between code and documentation. Now the question is, how can design rules be expressed in a checkable format? Developers make choices when they write code, and these choices are called design decisions. Design decisions impose constraints on code, which are called design rules. For example, in this design rule, the method save from a persistent framework should be followed by another method now, so that the changes are committed immediately. We can express design rules in the if-then structure, which helps in translating them into a checkable format. The if part describes when the conditions are met, in this case, when the save method is called, and the then part describes how the constraints should be applied. In this case, now method should be called. We call the if part a quantifier, and the then part the constraints of the design rule. Design rules vary in scope and the level of complexity. There are statement-level design rules, higher-level design rules, and architectural design rules. The example that I described earlier is a statement-level design rule. Higher-level design rules impose constraints on a few components. For example, a design rule may describe how a subclass of a specific class should be implemented. In this design rule, a subclass of artifact class should be marked by subclass annotation. Architectural design rules impose constraints on several components of the system. For example, the implementation of the sharded architecture is scattered in several components. This design rule imposes many constraints, but it can be broken down into smaller design rules. One design rule may describe how the request for persistence should be handled, and another design rule may describe how the persistent process should be executed. A common theme between all these design rules is that the quantifier and the constraints of these design rules can be expressed and represented as AST patterns. For example, if we look at this design rule and consider its code snippet, the AST of the code looks like this, and the design rule can be expressed as queries that matches specific elements of the rule in the AST. But how can we write checkable design rules as AST patterns? Existing rule checkers and defect detectors like PMD and findbugs allow developers to write custom rules as AST patterns. But let's see how a developer writes a custom design rule using an existing rule checker. Consider Alice, who is a developer and wants to write a custom rule for a system implemented in the model view controller architecture. The design rule Alice has in mind limits the type of information in the controller classes accessible to the view classes. Alice can easily detect the pattern of this design rule in a sample code she is looking at. She decides to use PMD to check this design rule. She looks at the official documentation of PMD and she realizes that there are two approaches to write new rules in PMD. One is writing an XPath query and the other one is using a Java visitor. The documentation says XPath queries are expressive, so Alice decides to write the design rule in XPath queries. She opens the PMD Designer, which is a utility tool for writing XPath queries, but she gets confused and is not sure how she should use the tool. She finally understands that she should write sample code in the tool. The tool immediately visualizes a very detailed abstract syntax tree of the code. Looking at the abstract syntax tree, Alice gets overwhelmed and she doesn't know the meaning of each node in the tree. Now she should write an XPath query, but she doesn't know how to do that. After looking at a couple of online resources, she manages to write an XPath query, but the feedback she receives from the tool is not helping her. She is not sure whether the XPath query she wrote is correct or not. So the current approaches to write checkable rules do not offer much support, and in this work we address this challenge by proposing new approaches to write checkable design rules as AST patterns. We introduce approaches that are simple so that inexperienced users can use them easily, and they are expressive so that they can cover most rules. Now let's start with finding a simple approach. All developers know code. Also, patterns of design rules can be shown through code snippets, as it is already done in traditional documentation. But not all elements in code snippets are relevant to a design rule. And the challenge is that if all irrelevant elements are removed from code, the remaining code snippet is ambiguous, and we cannot determine the type and role of the remaining elements. So we need an approach to address this challenge. We introduced the snippet-based authoring technique. The idea behind the snippet-based authoring is that code patterns can be written in a template, and only relevant fields can be filled for each design rule. But there is a challenge in the snippet-based authoring. Consider this example. In this pattern, the return type and the name of a method are specified. But how should this pattern be interpreted? Should both these conditions hold together, or only one of them is sufficient? So, we need an expressive approach to address this challenge and clarify ambiguities. Natural language is natural and is also expressive. But the problem with natural language is that it can be ambiguous. For example, consider this design rule. This design rule expresses that in controller classes, the method type should be void or it should be getter or search. We can understand this rule. But how does the tool know what it refers to, or how to combine these conditions? Some tools try to address this issue by introducing complex query notations like PMD. But the query notations are unnatural and hard to learn and understand. So we introduce a new technique, semi-natural language authoring. In this approach, design rules are expressed in a semi-natural language, which is close enough to natural language so that it can be understandable to developers. And also, the rules can be mapped to query notation so that they can be unambiguous and the tools can check the rules. The language should meet some requirements and be able to match queries like elements, such as class and method. It should also be able to match queries for elements with specified values, for example, when the type of a method is void. In some queries for an element, the AST pattern or the AST child is specified, and the language should be able to match these queries as well. In other queries, for some elements, multiple AST children are specified. In this case, the combination of the AST children should be clear in the query language. So, to avoid ambiguities, the conditions can be combined by and or and parentheses. And finally, the language should be able to match design rules. As we described earlier, each design rule consists of a quantifier, which describes when the design rule conditions are met, and constraints, which describe how the constraints of the rule should be applied. In the query language, these two parts are matched separately, but are expressed together with must-have. So we introduced two techniques for authoring design rules. One is snippet-based authoring, which is simple, and the other one is semi-natural language, which is expressive. We implemented these two techniques in a tool called RulePad. The snippet-based authoring technique is implemented in the graphical editor, and the semi-natural language authoring technique is implemented in the textual editor. Now consider Alice, who wants to write some design rules in the RulePad. This is the first design rule she wants to write that says, if a controller class has a method, then it should be a void method or a getter or a search method. Alice has never worked with RulePad before. When she opens RulePad for the first time, the tool displays a brief tutorial that describes each element of the interface. After reading the tutorial, she has started to write the design rule. Here you see there's a dynamic guide which describes the required steps for authoring a design rule. Alice starts filling the relevant fields of the design rule in the editor. As you see, the progressive disclosure in the graphical editor helps Alice to find the elements easier by reducing the clutter and showing the elements that are interesting to Alice. Now Alice wants to fill the method name, which should start with get or search. When Alice clicks on the name of the method, a pop-up tutorial describes how pattern matching can be used to write this condition. Alice specifies the constraints of the design rule by clicking on boxes, and the constraints get blue. Now that all elements of the design rule are filled and marked in the graphical editor, RulePad generates the textual representation of the design rule in the textual editor. But the design rule is not what Alice wants, so she changes the logical connective in the editor. Alice looks at the violated code snippets and realizes that the design rule she wrote is not accurate. Using the information from code snippets, she edits the design rule and adds missing values, and submits the rule. The second design rule that Alice wants to author says, if a class is in a controller class, then it should be private. Alice decides to author this design rule using the textual editor. The design rules in the textual editor must follow a specific grammar. The grammar used in the textual editor of RulePad consists of 27 rules and covers 16 elements. Alice has seen how the previous design rule was represented in the textual editor, but she doesn't know the grammar completely. The autocomplete in the editor helps Alice author a design rule following the grammar. After writing a design rule in the textual editor, RulePad populates the elements in the graphical editor. To check the design rule, she reviews the tokens in the design rule through the in-context documentation, and the matched elements in the graphical editor with the tokens in the textual editor. When she is confident that the design rule is correct, she submits the rule. The two editors in RulePad are bidirectionally connected. That is, if you make changes in one editor, the changes also reflect in the other editor. This connection has benefits. First, it helps to resolve ambiguities, which cannot be done in the graphical editor, but can be addressed in the textual editor. It also helps developers learn the grammar by looking and matching the elements in both editors. Now let's see how this connection is implemented in RulePad. When the user makes a change in a graphical editor, the graphical editor parser modifies the text in the textual editor. Alternatively, if the user changes the text in the textual editor, the grammar parser parses the text, and using the parse tree, the elements in the graphical editor are generated. To create a checkable design rule, the text in the textual editor is parsed by the grammar parser, and then the parse tree is translated into XPath queries by the XPath generator. The XPath queries, along with other information, create the design rule. RulePad also provides instant feedback for design rules by checking the rule against the code and extracting its snippets from the code. We evaluated RulePad in a between subjects user study comparing it with PMD. We recruited 14 students who were senior undergraduate or graduate students in our institution. In a survey, they all reported having prior experience in Java, having 1.5 to 10 years of programming experience, and 0 to 4 years of professional experience. Using the information we collected in the survey, we used stratified sampling to randomly assign the participants to the control and the experimental groups. We gave both groups the same training task to extract 3 design rules from a code base. The purpose of this task was to familiarize participants with the code and help them practice the if and then structure of design rules, which is necessary for writing design rules in the tools. The participants were given 20 minutes to finish this task, although they all finished in less time. In the main task, participants were asked to write 4 design rules. The design rules were extracted from an existing code base, bank application, which has 4,000 lines of code and 62 Java classes, and is written in the model view controller architecture. 3 of the design rules were predefined with different levels of complexity, and the 4th design rule was participants' choice from the ones they extracted in the training task. The main task was 80 minutes long and think aloud. At the end of the study, we conducted a semi-structured interview. To evaluate the authored design rules, we needed to use a common representation between the tools. As both tools represent the rules in XPath queries, we scored the authored design rules by scoring the query elements in the XPath queries. For example, consider this design rule, which is one of the design rules from the main task. This design rule has 6 query elements: class, class field, private class field, class method name, and class method name get 3 dots. Also, there shouldn't be extra query elements in the design rule. On the right, you can see the XPath queries corresponding to the query elements listed on the left. We considered the required query elements for each of the design rules in the main task. We found that design rules authored by experimental participants included more query elements compared to the ones authored by control participants. On average, experimental participants wrote 52% of the required query elements compared to 4% by control participants, which is 13 times more query elements. Since the fourth design rule were different for each participant, we scored them individually. Control participants didn't author any design rule as the fourth rule, and on average, the design rules written by experimental participants scored 72%. We also looked into the time participants spent on authoring design rules. We found that experimental participants finished their tasks significantly faster than control participants. In the post-study interview, we asked participants to rate their willingness to use the tool they work with in the study, and experimental participants reported that they are significantly more willing to use RulePad in their everyday work. Control participants faced some challenges when they were using PMD. For example, they had difficulties in understanding the purpose and the type of input for different fields of the PMD designer. They also reported that the documentation didn't offer adequate information for required steps and actions in the tool. Participants also mentioned that the errors were handled poorly by the tool. Experimental participants also had some experiences when using RulePad. They reported that the tool's features were useful, like the template in the graphical editor, the pop-up tutorial in the tool, and the readable format of the rules in the textual editor. We also observed that all experimental participants used the textual editor to verify the rules they wrote in the graphical editor. So, to summarize, we know that traditional documentation and code are disconnected, which causes documentation to be out of date. We proposed a new approach called active documentation, which integrates code and documentation by making design rules expressed as checkable constraints. But existing tools do not offer enough support for writing checkable design rules, so we propose alternative approaches. The approaches to authoring design rules should be simple and expressive. We proposed a snippet-based authoring technique, which is simple and helps developers write design rules in a code-based template. We also introduced the semi-natural language authoring, which allows developers to write checkable design rules in a semi-natural language that is close to natural language and can be mapped to query notations. We implemented these two techniques in a tool called RulePad. We evaluated RulePad by comparing it with PMD and found that using RulePad, participants authored 13 times more query elements in significantly less time. Also, participants reported that they are more willing to use RulePad in their everyday work. You can check out RulePad in a demo available online. Thank you.